Hello guys, today we're going to go over 2.2 and pretty much the area under the curve, density curve, standard deviation, a couple of other things. Now first of all, when do we use a density curve to display data? Pretty simple. When there's a regular overall pattern, we use a simplified model to pretty much describe it. And that model is called the density curve. Now, one thing that some students forget is that the area of the curve has to be equal to a unit, 1. And there are a couple of curves. First of all, we're going to focus on the one called the uniform density curve. And it's called uniform because it's pretty much perfectly horizontal and everything is under that curve. This is the x-axis, and this would be the top of the curve, and it's perfectly horizontal or parallel to the x. That one's called the uniform density curve. So how does this curve work? It's pretty simple. If you realize or you look at these two lines, you should note that they make up a quadrilateral. Could be a square, could be a rectangle. So if the area in here has to be 1, there's a couple of ways to do this. First of all, we always look at the x-axis. They give us an example in the book, and the units go from 2, 3, 4, wow, okay, very improperly scaled, 2, 3, 4, and 5. These are the numbers that are given in the book, from 2 to 5. So if you pay attention or you just count, I have 1, 2, pretty much 3 values. Even though there are 4 numbers, there are 3 intervals of data contained within this particular graph. So if there are 3 and the area has to be 1, what number do I put as the height to end up with a 1? It's pretty simple. 1/3. Because 1/3 times 3 intervals gives you a value of 1. So this interval would be 0.3333, this interval would be 0.3333, this interval would be 0.3333 of all data sets. So again, depending on the number of intervals in the x-axis, the height will vary. Let's say, for example, I have 4 intervals now. I go 0, 1, 2, 3, 4. Since I have 4 intervals, I have to multiply by 1/4. Oh my God, that is the height. Now, some people are saying, why do I care about the height? You'll need the proper height later in order to find the area under the curve. But it's pretty straightforward. So if I have 4 intervals, the height has to be 1/4, because 4 times 1/4 will give this quadrilateral an area of 1. Very nice numbers here. So depending on the number of intervals at the bottom, you're pretty much going to multiply by the reciprocal. If there are 7 units down here, you multiply by 1/7. If there are 2 units down here, you multiply by 1/2. Now some students are saying, why do I need that? Well, it's pretty simple actually. Let's go over a particular example. Let's say I have, I don't know, the same one in the book. I have 3 units. But let's go from 0 to 1, 2, and 3. I know that my height is 1/3. Okay, and this is a uniform density curve, perfectly horizontal. The reason you need the curve is because if you want to find the area under the curve, you just find the area of the quadrilateral. Let's say I want to find the percentage of values from 0 to 1.5. It's quite simple. The area of this quadrilateral is base times height. The base is 1.5 and the height is 1/3. So pretty much you multiply this, you get 0.5. Pretty much half of the area. So all you have to do to find the area under the curve of a uniform density is find the area of the quadrilateral they are asking. Let's say, for example, I want to find the area or the proportion of measurements between 1.2 and 2.3. I want to find the area between 1.2 and 2.3. Well, first I have to find the length of the base, and it's the difference between these two. 1.2 or 2.3 minus 1.2, because again, it's absolute value, let's say length, I would end up with 1.1. The length of this base of this quadrilateral here I'm trying to find the area of is 1.1. I multiply that by the height, and that's going to give you the proper area. I don't have a calculator at hand, but I don't know, 0.35, 0.37, something like that. You can just figure it out, calculate perfectly. And that's why you need the proper height, because using the base of the quadrilateral, or the amount of area you want to find, and or using the length of the values you want to find and the proper height, you can find the area under the curve. Since the area is 1, again, that's the proportion. If you end up with a decimal, 0.37, and you multiply that by 100, you end up with a percentage. So again, that's how you find the area under the curve of a uniform density curve, which will create a quadrilateral. That's pretty straightforward. So let's continue now with the mean of a density curve. But I want to skip a couple of... I want to go over the normal values. Just give me 1 second. Okay, let's go over the normal distribution curve. You've been seeing the normal distribution curve with me for the last 2 years, but again, now let's just review it officially. Now, first of all, a normal distribution is described as a symmetric, single-peaked, bell-shaped density curve called normal curve. Any normal distribution is completely specified by 2 numbers, the mean and the standard deviation. So we remember normal distribution curves are bell-shaped, they are symmetrical, again, mostly symmetrical. They can't be perfect, well, they could be perfectly symmetrical, but mostly symmetrical. They have a single peak, and they are defined by the mean, mu, and the standard deviation, sigma. We saw that in 10th and 11th grade. We're gonna go a little bit deeper into that today. So now that we've discussed what a normal distribution curve is, know that it could have different shapes. And again, we've gone over the shapes. The normal distribution curve could be skewed to the left. Again, remember, the tail end points towards the skewed. It could be single peak skewed to the right. It could be roughly symmetric, double peaked. And again, this would no longer be a normal distribution. These are just distributions. None of these are normal distribution curves. These are just distribution curves. This is a distribution curve that's skewed to the right. This is a distribution curve that's skewed to the left. This is a double peaked symmetrical distribution. This is a normal one. I'm trying my best. This is a normal distribution, okay? Now, when we go over the mean and median of a density curve, you have to think of 2 things. The mean would be the point at where, if this were an actual object, it would more or less balance. So if this is the curve, we can say that the mean would be more or less in the middle. It would more or less balance here. If I have a skew to the right, again, it's kind of difficult to just eyeball it, but the mean could not be here in the middle because it would tilt totally towards the left. So the mean is somewhere here maybe. It can't be also here right at the peak, because then I would tilt towards the left. So it is slightly to the right of the peak. And remember, extreme values pull the mean in that direction, but the median is resistant to that change. So every time I have a skew, the mean will be pulled in that direction, but the median will stay closer to the peak. It is still slightly pulled to the right, but it will be closer to the peak than the mean. So again, the mean is the place where the curve would balance if it were a real object. The median is pretty much the line that divides half and half, and that is slightly pulled by the skewed, but not so much. And it will almost always never be at the peak, but slightly to the right. Okay. And to find now the area under the curve of a normal distribution, again, normal distributions, you actually don't care about the height. That's only when we have a uniform density curve. When we have a normal distribution, let me try to draw this a little bit better. We use what we've been teaching you since 10th grade. We use the 68, 95, 99.7 rule. What that means is, if you have a normal distribution and your mean 68% or 0.68 of all measurements should be within 1 standard deviation of the mean. So 1 standard deviation of the mean should contain 68% of all values. That means this particular interval is 34%, this one's 34%. Now, within 2 standard deviations of the mean, you should have 95% of all values. And 95%, the difference between 68 and 95 is 27 points. 27 points, and 27 divided by 2, because I have 2 of these particular intervals. 27 divided by 2 is, I'm a little slow right now, 13.5. Okay, 13.5, 13.5. Then, within 3 standard deviations, I have a total of 99.7% of all measurements. That leaves that leaves 2.5 here, 2.5 here and 2.5 here, more or less 2.5. It's a little different, but you can just average it out to 2.5. After the 95, it's 2.5. Está bien. Pero 1 standard deviation from the mean, 68%. 2 standard deviations from the mean, 95% of all values. 3 standard deviations of the mean, 99.7. That's pretty much it. And how do we work with the standard deviations and the means? How do we draw the curve and the values? Pretty much, again, as I said before, a normal distribution is specified by only 2 values, the mean and the standard deviation. If I have a mean of 10 and a standard deviation of 2, or better yet, a mean of 10 mu, standard deviation of 2 sigma, you would put the 10 in the middle, and then I would add 1 standard deviation, 12. I would add 2 standard deviations, 14. I would add 3 standard deviations, 16. And on the left-hand side, I would subtract that standard deviation from the mean. So here I would have 8, here I would have 6, here I would have 4. So again, 68% of all values fall between 8 and 12, which is 1 standard deviation above the mean and 1 standard deviation below the mean. 95% of all values fall between 6 and 14, which is 2 standard deviations above the mean or 2 standard deviations below the mean. And almost all, not all, but almost all values, 99.7, should fall between 4 and 16. 99.7. We will discuss in tomorrow's video how to calculate the area under these curves, but it's pretty straightforward as well. So right now, that's it for today. Take care.